Good afternoon. Do you hear me now? So my name is Keisuke Saito from Rigaku. Yes, let me check. Yeah. Yes, so first of all, I'd like to thanks to organizers as a GFX for helping organize this workshop and also for giving us this opportunity to discuss our presentation here, our solution, let's say. Once again, so my name is Keisuke Saito from Rigaku. So I'd like to discuss what we are working towards as micro area X-ray diffraction today in this presentation. So one example is MLCC. This is a multilayer ceramic capacitor. So we are trying to evaluate residual stress on this MLCC capacitor samples. So the biggest motivation for us to work on this micro area diffractometer is, as you know, most of the electric components are becoming smaller and smaller. One example is MLCC. And so this is a BTO titanate-based MLCC as an example. So it shows sometimes like impurities. This black spot here is an impurity with a microscopic image. So scale is about 100 micrometer. This OH powers. And so people investigate like elements by the SEM, IEDS, or EDS. And also people will see, so this black area is made from barium and aluminum, titanium, oxygen. So then people try to figure out what kind of crystallography exists in this black area. But of course, you may go to synchrotron, but as Professor discussed at the beginning of this workshop, synchrotron is moving. The synchrotron, you need to block your time, and so hopefully you get some beamline time after 6 months or so. So people try to evaluate the sample as much as they could on a level-based diffraction. So that's what our driving force to develop micro-diffraction towards electrical application. So then, the final goal is to figure out what kind of polymers, including the barium, aluminum, titanium oxide, found by EDS, or SEM. So this is our goal. However, I also mentioned. So, however, as we know, generally speaking, the minimum beam size achievable on the level-based diffractometer is around 100 micrometer diameter spot, which is slightly too large to investigate such impurities on the MLCC, for example. So that's why our goal is to develop a diffractometer which provides smaller than the 100 micrometer beam size as a sample surface. And even moving your samples to achieve some of the measurement like action stress measurement beams, I mean the beam should eliminate the constant place on the sample. So this is our goal. Yeah, so one application like a residual stress measurement, I remember Professor this morning also discussed how we measure the residual stress by X-ray diffraction. So one of the different method is called side inclination method. So where we do sample plus tilt, right, incline your sample towards the incoming X-ray beam. And so the biggest challenges here is in on the level-based diffractometer, we have so-called open-cradle. So means the cradle support like a 0-90-degree tilt angle. And this place is occupied by sample state together with the sample part. And once you tilt and rotate the sample, there is a so-called sphere confusion, which is about 50 micrometer. So this is the smallest achievable 50 micrometer sphere confusion on the level-based diffractometer. So unless you may pay more money to have a high accuracy like a cradle, right? So the 50 micrometers, let's say, is the best compromise accuracy we could achieve on the open cradle. Of course, the other solution might be like a closed cradle. So 0-360 closed cradle. It's much easier for us to achieve the smaller sphere confusion. But so this may create some kind of block. I mean, so this may block X-ray beam depending on the geometry. So that's why we want to stick to the open cradle design. So the goal is to minimize this 50 micrometer sphere confusion to have a smaller beam size. So this is one of the biggest challenge for us. So this is our solution. So we just introduced a so-called micro XRD lab. So it has a couple of unique features. So first of all, so on this diffractometer, so you can change beam size starting from 10 micrometer diameter beam size as a sample surface up to 500 micrometers. The beam size is changeable. So it's dependent area where you want to illuminate X-ray, so you can control the beam size. And then, of course, by having such a small beam size, the flux matters. So it means how many photons per square millimeter matters, right? So because we want higher flux to achieve the measurement in a reasonable time scale. And to do that, so we do have a technology which is called rotating anode. And Micromax 007 HF provides 70 micrometer focal spot area of electron beam on the anode surface, and where we apply 1.2 kilowatt this area. So that's why the power density is much higher if you compare to conventional X-ray source. And then, so we were successfully developing the open-cradle open design with the spheres confusion smaller than 10 micrometer. So this is of course necessary to have 10 micrometer beam. And then, so we combine a hybrid 3000 detector, which is 2D hybrid pixel array detector, which is made from silicon, like pure substrate and X-ray illuminated silicon substrate, generates all electron pairs. And application specific integrated circuit ASIC counts the number of electrons generated on the silicon substrate. So this is the technology behind. So we have a 2D detector to count. So this is actually 8 centimeter wide, 4 centimeter wide detector to collect more intensity as much as we could from the sun. So this was an idea. So this is optics. So we about optics. So we do have multi-layer coatings, so which is called ERA, and we do have side by side. So means we have two parabolic cards. The surface of this has a parabola card, and we combine two of the mirrors, like a 90-degree tilted orientation like this, and the X-ray from the source. So this red spot in the source twice reflected by the mirrors from the green and the green. And so that X-ray is collimated, focusing towards this of the surface. This is how we achieve small the beam size of the surface. And just for the comparison, so the smart lab system could have 90 watt high power X-ray source. And so it has like a double keyhole collimation combined with 0.2 millimeter diameter keyhole. This is the first keyhole, and 0.1 millimeter diameter. This is the second keyhole. This smart lab is a general purpose detector for general applications. So that's why it has a line focus beam. So it means the X-ray shape is like a line, so which has a 10 millimeter wide, 1 millimeter height. So this is collimated by the double keyhole configuration. So compared to this configuration, right, so assuming this is a relative intensity scale 1, so on this micro XRD lab, 1.2 kilowatt, microfocus source here, side by side, confocal mirrors here. So it achieves 100 times more intensity. This is a standard reference material for NIST 640 silicon powder, and this of course is a diffraction 69 degree. And yeah, so we achieved 100 times more intensity. And we have a mask after the side-by-side mirrors. And if you move this the mask a little bit far away from the X-ray beam, so you can match the intensity and the flux from the optics and the source. So then you could achieve maximum 300 times more intensity compared to the double keyhole configuration. But as you see, there is no peak separation between the kappa and kappa 2 means resolution is compromised. And of course, the intensity resolution always is a trade-off. All right, so then spheres confusions to achieve less than 10 micrometer spheres confusions. So what we are doing is, so we found by the open-cradle system, it's very difficult to achieve less than 10 micrometer sphere confusions. So that's why we decided to have like a fraction matrix. So depending on phi and chi, the phi is the rotation, the chi is the tip. So depending on phi are the angles. So the software is going to have like a fractional table, and the software is going to drive X1 stage behind the sample to have the constant area for the X-ray illumination. So by that way, so the X-rays kept constant in terms of the illuminated. So this is a proof of the concept. So we have a needle here, and we tilt and rotate to guarantee right. So the X-ray illuminator and the cradle has a small spheres configurations. All right. So this is talking about detector. So as I briefly discussed, so we have a 2D hybrid 3000 detector. So which has an 8 centimeter wide, 4 centimeter high. And this longer side of the detector covers approximately 30 degrees. It depends on the distance between the sample and detector. But roughly speaking, it covers 30-degree range. So then by the 2D detector, so as you can imagine, so what you collect is like a part of the devariant. Unfortunately, it doesn't record 360-degree devariant, but as you see, it records a part of the devariant. So this means not only the data intensity information, like about the diffractometer, but also you can discuss like a frequency orientation, like a grain size or crystalline size. And yeah, because if your sample is powder, so your sample shows like a beautiful devariant, part of the devariant. But if your sample has like a coarse grains, so you will see like a spotty diffraction, not like a single crystal. So if you have a thin film or textured material, so you see like a non-uniform intensity distribution over the devariants. So by having the 2D detector, you get not only the phase information, but also texture as well. So this is quite advantageous if you measure texture, of course, and the residual stress as well, because sometimes you may have some difficulty to find out the peak. And I remember some of the professors discussed before the lunch, if I remember well. So she was struggling to find out the peak and assuming different crystal structures in the tree, right? So if you have a bigger detector, so all the diffraction spots are recorded by detectors. So it's going to help to find this peak. But the majority reason for us in this specific example, like a micro area residual stress measurement, is to collect more X-ray photons from the sample because an X-ray beam is quite small. So that's why we try to maximize the intensity out of the small area. And this is a comparison between classic, like a phone detector, no detector, recorded for, I think it's a scale 2 to 1 peak, 140 degree to theta by upper radiation. I think a batteries go and you have a AAA batteries. Okay. Yeah, so this is 1 minute data recorded by phone detector. This is 2D data recorded in 1 minute. So this is intensity from the intensity scale. The 2D detector corrects more intensity. So this will speed up the micro area, the measurements. So this was a reason for us to have this 2D detector. Okay, and this is the same sample. So as the image on the first page of my presentation is today. So there's a black spot in the microscope image, which has about 1 micrometer diameter. And then outside is white, which is supposed to be very tight. And so this is a comparison between the different places. So first of all, there's the green here. So maybe I can use a mouse. Do we see the mouse? Yeah. So this green area is the white area. So it's supposed to be very tightened. And then this is approximates illuminated area by X-ray. And so the green pattern here is purely from BTO3. So this is a perovskite barium titanate together with barium aluminate as well. So the aluminate peaks are quite small here and there, but this is a mixture between BTO and the BAO. And then we moved to the black area, and we had the high power setting, the high flux setting, slightly bigger the X-ray on the sample surface, which is in blue. And the red is the minimum beam size, so which was like the 20 micrometer on the sample surface. So then we compared between. So the blue is slightly over illuminating from the black area, so that's why it is a mixture between the white area, the diffraction pattern from the white area and the black area. The red one is purely from the black area. So what we found is some polymorphs based on the barium and aluminate, and the barium and the titanates are consistent of this black impurity area. So this is one of the example how the supplier of this MLCC chips are investigating the impurity of the BTO-based MLCC. All right, and then one of the other application that could be achieved by this micro diffractor, that is a GID. So GID stands for grazing incidence X-ray diffraction. So it means the incident angle is kept very low. For example, 0.5 degree. Normally we fix around the 0.5 degree. This is the incident angle, maximum 2-3 degrees depending on the density of the materials. So it means if you have the 2D detector, right, so the footprint matters. So footprint besides the resolution. because the 2D detector doesn't have any collimating devices between the sample and the surface. So it means all the X-ray from the sample is hitting the detector surface. If the footprint of the beam is big, the diffracted profile becomes broad as well. So that's why we have to have very small footprint on the sample surface to get reasonably sharp diffractogram in the case of 2D detector. So on the standard configuration, it's impossible to achieve GI XRD by the 2D detector because the footprint to be is going to be very large. So it means every diffracted peak is going to be broad, right? So you cannot separate the overlapped peaks. But as you see here, so if you have a small beam, so you can use the 2D detector even for GI XRD. And I would say that it's reasonably sharp. So this example is recorded on the indium tip outside. This is a transparent electrode film, which had 8 nanometer only. And on the left-hand side is the conventional, right? So the symmetric data, like alpha scan with the 2D data. Because of the 8 nanometer quite thin thickness, so from the symmetric diffraction, so you cannot get any diffraction peaks except the highest peak from the IPO. But by the GRD, because the penetration of the X-ray is limited to the very thin layer on top of the glass substrate, so that's why we were able to identify more peaks compared to the symmetric diffraction. So then residual stress, I don't think I need to go to very details because this has been discussed in this symposium. But we simply apply sine-squared psi method to measure the residual stress in this example. So what we do is just we tilt the scattering vector K step by step compared to your sample surface and then we try to see how to detect what this space moves depending on the tilt angle of the scattering vectors, right? From the perpendicular to the in-plane direction. And from the slope of this sine-squared psi versus 2 theta about this space plot, from the slope and from the stress constant K, so we can evaluate the residual stress on the materials. All right. For residual stress measurements, so generally speaking, we have 3 different configurations can be achievable by the level-based detector. On the left-hand side, which is called side inclination. So it means your sample is tilted perpendicular to the incoming XRD. And ISO or ISO inclination method, plus psi and minus psi. So those are the 2 different the setup on the right-hand side. So in this method, the second vector is tilted in the theta of the diffraction plane. So it means by tilting, by changing the omega angle, right? So you can tilt the scattering vectors. And the plus method has a higher incident angle, so the minus psi has a lower incident. So in this picture, I hope you see a collimator over there, and X-ray is coming from the left and hitting the sample on the right-hand side. So obviously this has a higher incident angle because the sample is almost perpendicular to the collimator. This is almost parallel, right? So this is negative psi. So the table here just approximately, we try to show you what will be the shape of the X-ray beam on the sample surface. So, for example, by the side inclination, of course, the beam shape on the sample surface is becoming like a broader, right? With the higher, with the tilting more by your sample, right, towards the incoming. And the psi method, plus psi iso inclination, so keeps the beam shape smaller compared to the other 2 methods. So that's why we normally use this psi plus psi method iso inclination geometry for the residual stress measurement because X-rays are kept small on the sample surface. And this is how we measure the residual stress by using the 2D detector high peaks. So as we discussed, so you can get part of the varying. So this example is like varying tight rate 3 to 3 diffraction. So normally we go to very high angle diffraction to get more accuracy in the D-space determination. And this is a 2 theta angle 128 degree. And so you see a beautiful varying from the varying tight rate. And on the software wise, so we split the varying into a couple of different regions. And the software integrated intensity and try to fit a profile like this by profile fitting procedure. And so the purpose is to get the deformation of the varying because of stress as precisely as possible. So that's why we split the wavelength into several different regions and integrate and calculate the peak positions, and software tries to fit the wavelength to extract the stress information. So this is called 2D residual stress. So then we apply the triaxial stress measurement. So means so this is the stress tensor 3 by 3, starting from sigma 1, 1, 2, 2 along the y direction, 3, 3, calculated from the sample surface. And then shear stress like 1, 2, 1, 3, 2, 3. So those stress components could be determined by this triaxial method. But to do that, as you can imagine, so we need to rotate and tilt very fine steps like this. So this is a table of the phi and psi configuration used in this example. So totally, so we repeated 22 exposures, let's say, and not really scale. So exposure on this I try to extract the stress matrix. Exposure time of each frame a couple of minutes. So right, so to be honest with you guys, so this measurement could be like a couple of hours, right? So the measurement is not like this fast, but so we had 10 micrometer of collimators. The inside of the sample was 25 micrometer diameter. And then after a couple of hours, so we were able to determine the residual stress. So those are not our results. So just for information, the BTO. So this is how it looks like. So this is the MLCC. So it has like a terminals on both edge. So this is electrodes to your circuit board. So the inside of the MLCC, we have a stack between the dielectric materials, in this case marine type, and also internal electrodes, in this case nickel. So we have like a multi-layer structure, to increase the surface, because we know the capacitance is a function of the surface area. So we try to increase the surface to have more capacitance. And then, so this is the calculation. So based on this paper in 2008, so this is simulation calculation. So it is known the residual stress created in this MLCC capacitor because this is annealed right after the process, and because of the difference of the linear thermal expansion coefficient between nickel and iron titanate. So just FYI, since this is the endpoint, this is the thermal expansion coefficient for those materials. Because of the difference between, so when the temperature is decreased to the room temperature, the stress is generated, right? So and depending on the number of the layer stacks, so the black ones are 30 dp and the reds are 60, and the blue the 100 dp, and this is the cross section. This is the spatial information location across this blue, right? Across the terminal area. And so the negative stress, this means the compressive stress are generated on the BTO. And then it is known, so depending on the compressive stress, so towards this direction, this is bigger stress here, and this is electric field, and this is the relative conductivity. And so if we apply more stress, the capacitance is going to be increased. But if you have so much stress, this MLCC reaches the cracks, right, in the long-term operation. So that's why one of the purpose in the material design viewpoint is to find us the best, setting, let's say the best like residual stress in the BTO to have the best performance and yet, longer lifetime of the device. So this was the instrument setup. So let me introduce on the left-hand side. So this is an overview of the diffractometer setup. On the left-hand side, so we had the Micromax 007 HF, so which had 70 micrometer focus, both sides to be microfocus X-ray source, 1.2 kilowatt. So then we had a very max mirror, so it has a side-by-side and a 15 centimeter long parabolic mirror to focus X-ray beam. And we had a collimator, and then your sample is placed here. So the high-flux detector on the right-hand side. So you can change the detector distance automatically, motorized between 60 millimeter up to 150 millimeter. And in this setting, it is 150 millimeter. And just FYI, this is really important because the distance from the source to the sample is 600 millimeter, and detector size is variable. And this is a zoomed area around the sample. So this is your sample area here. And then we have some observation cameras so that you can control the sample position towards XRD by using the microscope, and you see your sample image on the display. So then laser diode illuminates the X-ray position, because unfortunately we can't see the X-ray, right? So that's why the laser simulate the place where the X-ray illuminate on the surface thing you just place to for the X-ray measurement. All right, and this is a result we got so far. So we are still working on this application development. So this is the only one available data that can be discussed in this presentation for now. So we have this kind of MLCC, as I mentioned, it's a stack of varying titrate nickel. So what we did is, so we measured this area, this corner area, and this is a microscope image. This is a 200 micrometer scale there. And then, so sigma 1, so X direction is like horizontal direction, 2 is vertical direction, 3 is perpendicular from this position. So the 1, 2 is the shear stress. And so this is what we got. And on the image, so I try to represent the stress by changing the direction of the arrow, and also by changing the size of the arrow. So means, for example, number 1, the 1 residual stress negative 80 plus minus 8 is estimated standard. And so that's why the arrow is heading towards the left-hand side direction, and the length of the arrow is approximately proportional to the residual stress, right? And so what we found is a quite large compressive stress on the place number 1 along the X direction. While, as you see, the shear stress 1, 2 also negative, and 2, 2 was positive. Right, kind of small stress we found, and on the corner, right? So it's active area means the layer stack, and on the corner of this MLCC here. So this had very different characters. You know, the 2 was negative, and 1 was very small, and the shear stress was kind of large compared to the position number 1. So this area is called like a BTO outer layer. So means this area is consisting 100% of varying titrate, low layer, and this has a width. As I mentioned here in the pictures, 100 micrometer width, and we try to illuminate this 100 micrometer width the BTO outer layer only, without illuminating the active area or outside of the outer layer. So yeah, so this is what we found. So let me conclude my presentation for today. And so I discussed micro XRD lab, and it provides between 10 micrometer up to 500 micrometer beam size active sample position, right? Not as end user polymeter. And then the flux intensity information I didn't discuss in my presentation is about 10 to the power 9. If we maximize the beam size, so means if you have a 500 micrometer beam, the flux intensity is going to be over 10 to the power 9. So then, so we also developed a 10 micrometer, less than 10 micrometers. We have the confusion to the open-cradle system to have constant illuminating position on your surface. So thank you so much for your attention.
Any questions from Dr. Saito? Yes. It's kind of a random technical question. So you chose to use a microfocus rotating anode. What are the pros and cons of doing that versus using a liquid metal jet with the microfocus?
Yeah, thank you, Professor. So the liquid metal jet source, first of all, the sources are limited, right? Because the metal must be liquid at room temperature. And so this is a conventional like X-ray source technology, but only the anode is sticking in the vacuum. So that's why this can provide a variety of the different energy of the X-rays, starting from moly, silver, cobalt, chromium, and copper applications. So this is one of the huge advantage. And then a liquid metal source has a very high radiance. So means the focus spot it could be smaller than the 70 micrometer. So this system has a 70 micrometer, and liquid metal could have 50 micrometer. But the power loaded to this area is much smaller compared to this. So that's why power density wise, so this may provide higher power density. But if you need a high brilliance, I would say the liquid metal just may provide a better brilliance. But if you need a flux, like this example, I have other diffraction, different diffraction, stress texture. So we need a flux rather than the brilliance. So in this example, this solution may provide a better solution. Thank you. Thank you.
All right, any other questions? All right, otherwise, thanks you so much again.
Thank you so much.